Okay, so we are going to talk about submodular functions, if I can get this moving. Okay, so we saw submodular functions in Hausdorff's talk. They are set functions. My universe is going to be denoted by capital N instead of small n. You'll see why. There will be integer valued, and a function is submodular if it has this decreasing marginal utility, which says that the this is like a discrete derivative. When I take a set S and I add an element I not in the set, if I add it to a superset, that derivative sort of goes down. So that's the notion of decreasing marginal utility. And we'll be talking about submodular function minimization with oracle access. You can only access the function value. And without loss of generality, we're going to assume that the empty set evaluates to 0. So in particular, if the empty set is not the minimum, then the value of the minimum would be negative. Okay. Okay. So that's the question. You want to find the set S which minimizes f of S, and it's a remarkable fact that it can be done in polynomially many queries. And this is a slide with I'm missing a lot of citations, I'm sure, but in general there are various ways of minimizing this. And as we saw in the last talk, currently the best known exponential time, but if I just look at the number of queries needed, n square log n queries are suffice. And this is, no one knows how to do better, and there is no lower bound better than 2 times n, and 2 times n was proved last year or this year, depending on when you go. But we are not going to talk about the query complexity of submodular function minimization in this model. Rather, this talk is about parallel SFM. So it's so the whole problem is via query access. And whenever you have query access models, there's a question of the rounds of adaptivity. So a non-adaptive algorithm for any query access model, in particular for SFM, will ask all the questions. The questions are fixed, and given the answers, depending on the submodular function or in general anything, the answer should reveal the minimizers. That's non-adaptive algorithm. And in general, an R-round algorithm, the ith round queries that you make to the submodular function can only depend on the answers that you've seen in the previous rounds. Okay, so that's what are the rounds of a query model algorithm means. And in terms of parallel algorithms, this is sort of like the notion of depth in a parallel algorithm. So we are interested in this question of, can we make efficient submodular function minimizations low depth? So this is the question. So in how few rounds can a submodular function be minimized, making polynomially many queries? And of course, if you don't have polynomial queries, the answer is 1. You can make all the 2 to the n queries and then find it. So all existing SFM algorithms, of which there were many efficient, they run in omega capital N rounds. In fact, maybe even more, but at least these many rounds. And if there's an open question to take from here is that needed? Can you actually do efficient SFM in small o n rounds? Now, turns out that it is not very difficult. In fact, if you spend maybe half an hour on this, you can prove that if you're non-adaptive, if you're making only 1 round, then you basically have to make exponentially many queries. Okay. On the other hand, even proving that 2 rounds you cannot do better is not trivial. Okay, and that's because the questions depend on the previous round's answer, and the sort of the possibility of algorithms explodes already. So even this is not trivial. And so it was quite remarkable last year, Eric Balkanski and Singer proved that any efficient submodular function minimization algorithm must require log n by log n rounds. Okay, and I'll present this framework because we build on this. So this does not rule out the fact that there can be polylog n round algorithms, but our result says no. The answer is, we will see today that any efficient submodular function minimization algorithm must make cube root n rounds. Again, I'll repeat, I don't know which way to bet, whether the answer is small o n or can this actually cube root n become omega n rounds. I don't know what the answer is, but that's, I think, a great question to figure out. Any questions about the results? Okay, so before I move on to the description of the details, let me put this result in some perspective. So if you look at, instead of submodular function minimization, if you just look at convex function minimization, so it's a non-smooth convex function minimization. And if you remember from previous talk about the Lipschitz, there's a convex function related to a submodular function, the Loas extension, and that's a non-smooth convex function. But if you look at general convex function minimization, there is a result, rather old result of Nemirovsky, which shows, again, the same cube root n log 1 over epsilon lower bound is needed to get epsilon close in some notion of closeness. And the cube root n is, well, it's a coincidence, but not quite, because the math, I think, is similar. And we'll sort of maybe say a little bit about it. But this might be n. We don't know if the answer is better than that. And there is also, so more recently, this question has seen a lot of work, and I'll not really talk much about it, but Aaron, Bubeck et al. And Aaron is one of the co-authors. So one of the results they prove is that if your depth of this algorithm is has to be less than root n, then gradient descent is the best thing you can do. Okay, so so if the dependence on epsilon is poly 1 over epsilon, the picture is slightly more complicated. Okay, so that's one perspective where this function problem falls of parallel SFM. The other thing is parallel SFM with the different m. So if you look at submodular function maximization, so that's a sort of a, like, what does it mean? As in, so it's an NP-hard problem in general. But if you look at problems like maximizing a monotone submodular function based on cardinality constraints or matroid constraints, there are various algorithms that have been developed. And you can ask whether they can be parallelized. So for example, if you have only a cardinality function of k, there's a greedy algorithm which gets 1 minus 1 over e, but greedy algorithm is adaptive. Can they be parallelized? And again, Balkanski-Singer in a different paper showed that no, you need the log n by log n to get any constant factor approximation, but log n does the trick. You can get 1 minus 1 over you can get a 1 minus 1 by e minus epsilon close in log n times some poly 1 over epsilon. So that's something that is known. But if you look at just unconstrained for a non-submodular function, a general submodular function, you want to get an algorithm. So there's a half approximation known by a beautiful double greedy, and that sort of can be parallelized and get a half minus epsilon in order 1 over epsilon rounds. Okay, so that's the status in about submodular function maximization. Yeah, yeah.
Those algorithms on convex functions, those are like independent.
Yes, so the number of queries are still, I think, a polynomial in every round. Okay, so this is, I think, called highly parallel in the notion of Bubeck et al. So you still need to be efficient. You don't want to make exponentially many queries in the dimension. Okay, but the number of queries is still polynomial. Okay, should remember to repeat the question. I will. Okay, so let me get into the proof ideas. Okay, so here's one thing that you need to, maybe one thing you take away are these special class of submodular functions, which I find really nice, which sort of capture the easiness of a submodular function. Okay, so take a partition of the universe, P1 to PR, and we call the submodular function partition submodular if the value of the submodular function only depends on the number of items this subset takes from each partition. Okay, so in particular, there's some function h, which is an r-dimensional function, which takes an integer vector of dimension r to some integers. And f of s is h evaluated on these s intersect P1. So how many elements it takes from P1, how many from P2, and so on and so forth up to PR. So that's a partition submodular function. And these functions were introduced by Balkanski-Singer and were used for proving lower bounds. And we'll see how they're helpful. In general, any subset S, it has a signature with respect to this partition. And it's basically xi is us counting how many elements from the part pi S contains. Okay, so f of s is in general going to be equal to h of some this integer vector x. So we're going to now talk about these h vectors. Okay, so that's a partition submodular function. And we can see in general, if the partition is just partition to trivial things, it captures all submodular functions. But if the parts are small, if there is only one part, then it's a very simple submodular function, just a concave function. So this changing the parameter r sort of changes the sort of quote unquote easiness of a submodular function. And I don't think these functions have been studied. Like you can ask how fast can these functions be minimized depending on r. And they're, I think, open. So we'll come to these questions maybe at the end if we have time, but that's the definition of partition submodular function. And what is the property on H we need? We basically need the similar discrete derivative property that if I take a point X and I increase one coordinate, then the marginal difference can only go down. Okay, so a cartoon picture to see this and keep in mind maybe is the following. So here there are R is 2, so it's a two-dimensional grid. And the edges here have the numbers here are the marginal. So how much the H increases when I go this way, how much H increases when I go up this way, these are the various numbers. And submodularity means that these numbers, if I go up or go right, they keep decreasing. And there's one other property you need, it's consistency, that in any square, if you take the right and top, those numbers should add up to top and right. So for example, 1, 2, and 2, 1. So that the marginals, if they have these two properties, that defines function. Why am I stressing this? Because I'm going to talk about the function only as marginals from henceforth. So in particular, if I give this picture and I ask what the function value is here, well, it is 1 plus 1 plus 0 plus 1, whatever. So you're following this path, and I think it evaluates to 1. And if I've done it correctly, every path here evaluates to 1. Okay. So any questions about what partition submodular functions are? Okay. So let me now say what the Balkanski-Singer framework is. So they construct a family of these partition functions which satisfies 3 properties. One, they need to be submodular. So the marginals need to satisfy this decreasing property. And second is that the minima there's only one minima of the submodular function, which is the last, in some sense, the PR. Okay, that is what one has to find. And their lower bound framework is this, that any efficient I-round algorithm will probably learn the first I parts, but then is completely confused about the rest. Okay, so let me clarify this. So H is a function which defines the function F, but when given a partition. But if I scramble the partition with the same H, I get a different submodular function. And what this is saying, so for example, the first round of queries that you make, and the partition is just a random partition, well, the first round of queries will reveal to the algorithm only the first part and will know nothing about the remaining parts. And remember, the unique minimum is the last part. So if it is confused, after R minus round, it will be confused about the last part in a big enough subset. And so it cannot, with high probability, return the last set. Okay, so these are the 3 properties that we need. Yeah.
Sorry, what do you mean by PR being the minimizer now? Because I thought you meant like the top of the rectangle.
Yes, so PR, so the partition function is P1, P2 up to PR. And the submodular function is minimized when evaluated the last part. So in particular, in the H, if you look at the H world, the H's minimum is the 0, 0, 0, comma, the size of PR. So H is minimized in this place. Okay, I'll come to a picture in a bit. So, but maybe this is the slide that is, yes, I'll pause here to see. So we want these 3 properties, submodularity and unique minima, and that's the framework of Balkanski-Singer, and the fact that you cannot distinguish in one, you cannot distinguish more in the future. So maybe the slide that I want to take, spend a little bit time, maybe the one slide that I spent time preparing is sort of to show the tension among these 3 properties. Okay, so imagine R is 3. Okay, and since it's painful to draw a cube, I'm just drawing P3 is the minimizer, and I'm drawing the hypergrid when P1 is 0. So I'm drawing this hypergrid. Okay, and for simplicity, let's assume the marginals are only -1 and +1, just to show the point. So what does the fact, so P3 is the unique minimizer, so empty set is 0, so this has to be negative, f of P3 is negative. So this point, which is P3 here, this point must evaluate to something negative. So it will be, the submodular says this will be some point will be positive and then it will become negative. And the point is that the length of this is going to be shorter than the length of this, strictly shorter than the length of this. because it has to be negative here. Now, the fact that queries cannot, single round queries cannot distinguish between P2 and P3 says what? Well, a single round, if you take a random subset, it will possibly contain equal number of P2 and equal number of P3. Okay, if P2 and P3 are randomly picked, you'll basically pick a point whose signature lies either on the diagonal or close to this diagonal. Okay, and the fact that you cannot distinguish, so this set is not a distinguisher, means if I sample this set and then I query all the other marginals, those marginals don't reveal anything about P2 and P3. So in particular, the marginal going up and the marginal going right at that point should be same. If they were not the same, then just the n queries will distinguish between who is P2 and who is P3. Okay, so again, maybe I'll repeat this. The diagonal is sort of saying the signatures of typical sets that you pick. And the fact that it's not a distinguisher means that if I query all the marginals, these marginals will not reveal. So the marginals don't reveal me who's P2 and who's P3. So these marginals better be the same. Well, submodularity says if this is negative, then this must be negative. It's only going to be smaller because I'm going up. And if this is negative, the fact that it's indistinguishable means that this is negative. And if this is negative, if I go to the right here, then I get negative here as well. Okay, so I have plus ones here, minus ones here, and then a lot of minus ones here. And that's a problem because that would mean that this point will be smaller value than this point because I have, say, 3 pluses, 7 minuses, and maybe 3 pluses, and again 7 minuses. So this function, when I travel from here to here, has actually gone down from here. So this is not the, so P3 is not the unique minimizer. So in particular, if P3 is not the if P3 is the unique minimizer, the counterpositive is that you will be able to distinguish between P2 and P3. So what's the catch? The catch is this picture is drawn with P1 equal to 0. So it's as if I pick a random set. If I pick a set which does not pick anything from the first part, but is equally randomly sampling between the second two parts, then there must be distinguishers. But that's not going to happen. If you pick a random set, you'll pick a lot of things from the first part as well. And that's the fact that Balkanski-Singer sort of exploit. And at an extremely high level, this is what they do. To make sure that you cannot distinguish between the second and the third part, they use the first part as what they call a mask. Okay, what does that mean? It means that when you pick a set, and if that set picks fewer than half the elements from the first part, then all the marginals in the second and third part are +1. You cannot distinguish using that set anything between P2 and P3. On the other hand, if you pick more than half the elements, then they suddenly become -1. Okay, so if you go back to this picture, it says that this kind of a picture emerges only after P1, you've picked half the elements from P1. And why is that? So this again, this will imply indistinguishability, but what's the issue with this? Well, again, now I want to go to P3 and P2 and expect and see how much is the value of the function there. The problem with this is, now consider a set, the full set, where you've picked up everything. Well, after picking P1 elements, everyone gives negative marginal. So I'll have -P2, -P3 out to -PR. And the fact that the whole set is not a minimizer means who is going to compensate for it? P1 must compensate for it. So P1 must be super large. So P1 must give me positive marginal maybe all the way through. And that will sort of counteract all the minus that I get. And that's, and then inductively, so P1 must be bigger than the sum of the rest, P2 must be bigger than the sum of the rest, which implies that the number of the R, which is the lower bound on the parallelism, cannot be more than log n. Okay. And of course, what I am lying here, this is actually the problem with this is you cannot get submodular functions with this property because consistency breaks down. So they need to do a smoothed version. The marginals are not -1, 1, they're much smoother. And there is the technical reason why they actually get a log n also in the denominator. Okay. So but the core idea was this. So maybe in one slide, what our observation was, is that we don't really need such a strong mask to fool an algorithm. Okay, so all we need is the following, what we call suffix indistinguishability. And it's capturing the fact that if you pick, so suppose you are in the beginning, you pick a random set and you look at the signature. Okay, so what do you expect? You expect to pick equal proportions from each partition. And you only need to fool such signatures. All the other signatures maybe are completely distinguishable. Okay, maybe all the other signatures can reveal anything about the partition. But if you have a vector whose proportions in every coordinate are sort of the same, then they should not reveal anything, which means that the marginals of this dj or partial j hx for j bigger than I, the things that you're trying to fool, they should only depend on the norm of x, which means that they're all the same and you cannot get anything. Okay, so just to sort of show why this differs from the Balkanski-Singer thing, now suppose if you're in the first round and you sample this point. Okay, so this is a point which does not satisfies this for I bigger than 2. Balkanski-Singer will say, well, you've picked so many points from 1, all the marginals here must be -1. It's very scared about revealing information that way. But we are just saying they all have to be equal, so they can all become +1. So you will not get this P1 bigger than the sum. The -1s will kick in much later. Because I understand this is a little hard to digest, but let me sort of say again the 3 properties that are enough. One is the 2 are from Balkanski-Singer, submodularity and unique minima. And the other thing that we need is that when vectors have equal proportions from every part, the marginals should be indistinguishable. So let me just describe my construction, our construction, and then maybe we will adjourn. So this is the construction. So the partition will be all equal size now. So small n is the size of each part, and there are r parts, and the total size of the universe is n times r. Furthermore, we'll actually have that the marginals are only going to be -1, 0, or 1. Okay? And I'm going to describe these marginals of these functions via an algorithm. Okay, and then we will see what the function is, but that is not very interesting or enlightening, I think. But I'll describe these marginals via an algorithm. So in particular, given any point x, so x is the signature of the set S, the marginals from 1 to r will look like this. It will be +1s for the first some numbers, then it will be 0s, then it will be -1s. Okay, again, 1 to r are the P1 to PR. Okay, and r is the minimizer. So the AX is the point where it flips from +1 to 0, and BX is the point it flips from 0 to -1, and this A and B will depend on X. It might not exist, in which case I have only +1s. So all the marginals are +1s. So now I'll describe how these A and Bs are picked. Good. So maybe this is the last conceptual thing. So for every coordinate t, from 1 to r, we'll be defining a function which depends only on the suffix x to n, xt to n. Okay, and I'll explicitly define what this LT is, but for now, it's a function which depends only on the suffix. It does not look in the prefix. And we will pick AX and BX, these 2 coordinates, to be the ones which have largest positive LT. Okay, if you are following it for now, and again, I'll maybe say a little bit, this part already implies submodularity. Because if I pick the largest LT and X actually increases, then the largest A's and B's will only move to the left. And that will imply submodularity. So that's the reason we look at things that depend only on the suffix. Okay, but this is how A and B will be picked. And again, it will be picked in such a way that there are chances that they may not exist because nothing may be positive, in which case all the marginals are +1. Okay. Good. So, sorry. Yeah. So I look at all the LTs. I look at the 2 largest. And if they're positive, I pick them. If they're not positive, I don't pick them. If there's only one is positive, there will only be AX, but no BX. So for example, if there is no BX, then it will be +1s and then all 0s. Does this make sense? Maybe a question here. So I'm defining 2 coordinates depending on X. And furthermore, it depends on, it's picking the maximums of these suffix functions. Let me just tell what the suffix functions are. So they look like this. So if tau was 0 and gamma was 0, this will be just the suffix sums. But it's the suffix sums. The tau is saying, I don't count you till you cross my threshold. The tau is some sort of a threshold. What's the threshold? The threshold is roughly n by 2. So till I come to n by 2, I'm not going to contribute to LTX, which might indicate that my marginal is going to be only +1. Okay, this is not quite true, but it's not going to contribute towards LTX. And we shade it a bit by what? By exactly the standard deviation. Why standard deviation? Well, when we say xi is around xi +1, but they can be off by 1 standard deviation in the random selection. So this is where the root n will come in. And then there's an offset which I subtract here. Okay, so that's maybe we'll see why this is important. But that's the function. So again, I have LTX for t going from 1 to r. A and b are the largest indices, and then a and b define the marginals as follows. So that's how the whole function is defined in one way. But if you do them, as in if you look at it and you can actually say what the function is explicitly. So you don't need to tell by the marginals. The function is this. Given x, I figure out this LAX and LBX, which are the largest LTs, and I cap it at 0. If they're negative, I don't. If they're negative, I don't count them. So I don't increase the function value. And I just decrement it from the L1 norm. Okay, this I don't think is super interesting that this is the function, but that's how the construction will show a few things. So I want to say why the 3 properties hold. So let me see if I can do it. So why is this function submodular? Well, this is because of the intuition I gave. If I have x, and x has these ax's and bx, note that they may not exist. And then I increase x. Well, if I increase x, the LTs can only increase. So the largest, and since I'm summing them up, the a's and the b's can only shift towards the left, right? Because I'm taking the sum of these things. So if these things are, if this thing is positive, then something, the maximizer can only move to the left. So when I move to the left, if ai and bi move to the left, then some +1s will become 0 and some zeros might become -1. So which means that the marginals are only decreasing. And this is true for any sort of any suffix function that you use, which is positive.
Just to be annoying,
yeah.
Like you're choosing the suffix. I mean, A and B technically correspond to the ones with the smallest t's. No, if you're moving to the left.
So the value of LTX. So AX is the coordinate t that maximizes LTX. So as you move to the left, you're hopefully picking more things because the suffix increases. When will you not move to, why is A not 1? Well, A is not 1 because this might be negative. But if this went from negative to positive, then I'll move to the left. Yes. And when increasing the coordinates, these A's and B's move to the left. Yes. So that's why it is submodular at an intuitive level. But maybe the more interesting thing is why is this sort of implies suffix indistinguishability? If I have these vector x which are almost the same, what happens? So if you look at it, and maybe I should have said that if I look at the first round and I have a vector x which is almost the same, what is almost the same? They may be off by √n, right? What's going to be the maximizers and the minimizers? Okay, so maybe there are two cases. One is they're almost the same, but they're small. And the other case is they're almost the same and they're large. So suppose they are all the same, but they are large. Large means what? It's bigger than n by 2 minus some few standard deviations. Well, if this number c prime is bigger than c, and I think that it's like slightly bigger than c, then all these summands are going to be positive because tau is smaller than that threshold. Well, what does that mean? Well, if they're all positive, then the maximizers will lie to the left of this thing, because everything afterwards is positive. So the maximizer will lie to the left of this thing, which means this AX and BX lies in 1 to I. Well, that means that the marginals following I are all the same, because they're either all -1 Or maybe A and B don't exist, in which case they're all +1, or maybe only A exists, in which case they're all 0. The point is that everything from I + 1 onwards is the same if they're all large. And if they're all small, if xi's are smaller than this value, then actually this LTX, and this is where the gamma comes in. The gamma is like roughly R root n. If xi's are small, then this thing is 0, is strictly less than 0, which means that the maxima cannot lie beyond I + 1. So they have to either the A and B, the maxima lie in the first I + 1, or maybe they don't even exist. In either case, all the margins are the same. Okay, so this threshold and this offset is constructed so that at this point, when all the xi's are the same, the maximizers A and B only lie to the left. And as soon as they lie to the left, all the marginals are the same. So this leads to suffix indistinguishability. And maybe finally, why is cube root n coming in? Well, when you look at the function this way, you want that the all ones function or the all n function should not be the minimizer. So if you calculate the value of the all n function, you will see that, and I'll spare you this calculation, but it's not that hard to see. It evaluates to n by 2 minus 2r root n. Basically, n by 2 minus 2 gamma. And you want this to be positive, which means that r has to be less than square root n, where n is a smaller number, which is a standard deviation for one part, and which means that if you look at with respect to the big universe, capital N is n times r, you get r is n to the cube root of n. So that's where the cube root comes in. So r, the number of rounds has to be one standard deviation of a single part. And I think something similar is also true in Nemirovsky's construction. Okay. In my remaining -2 minutes, I'll end with some questions. So can SFM be done in small n rounds? As I already mentioned, I don't know which way to even bet right now. Maybe square root n, maybe not. The other interesting question is, if I scale the functions to -1, 1 and ask for an additive approximation, what is the parallel complexity of this? So our techniques, so our functions have marginals -1, 0, 1. So they are between minus capital N and plus capital N. And they cannot distinguish between 0 and actually minus cube root n. So that gives some approximate lower bounds. And in particular, if you look at it, if you work on it a little bit more, we can get an omega 1 by epsilon. But we don't have, like, it's possible that if you want a constant approximation, you can do it also still in constant round. It's a possibility. But already you can beat n if you allow poly 1 over epsilon dependence. Then I would like to sort of throw out these questions that even for the special case of partition SFMs, where there is an R parameter, what can you minimize them something in like n plus poly R? Like if there are only constantly many partitions, can you do it in linear time in that case? And then finally, this is the question that even Hautian mentioned. What's the lower bound for general SFM? Can you prove anything superlinear here? Okay, with that, I'll end. Thank you very much for it.